Hi everyone, this is Mr. Lee. In this video, we are going to go over the final form of potential energy. We're going to revisit gravitational potential energy, but this time, the G is not constant. Okay, so this is another way of saying that we are actually out in space. All right, so let's begin. So let's talk about the idea of G being constant and G not being constant. So here on Earth, right, so if this is my floor, we say that the gravitational field is pointing downwards, right? It always points towards the Earth, and our G is a constant 9.8. I know in class we use 10, but technically it's like 9.81 meters per second squared, right? So this is a constant. So when we have a constant gravitational field, we use mgh. But if we were to go out in space, our gravitational field is not constant. So for example, if this is the Earth, and let's say we are to look at right here, at this point away from the Earth. Here, our G, it would be less than 9.8. But the further out you go, let's say the G here, so if we call this G initial, we call this G final, the further out you go, your G's decrease. Your gravitational field decreases. The Earth's influence all the way out there, it gets smaller and smaller and smaller. So in this case, your gravitational field value would change, so it's not constant. And we discussed this in a previous unit, but the formula will be Gm. In this case, the m will represent here the Earth all over r squared. So we see here that as our radius increases, if our distance away goes up, because this r is in the denominator, the G has to go down. The Earth's gravitational influence on you has to decrease. All right, so we're going to use that idea, and we are going to see what the gravitational potential energy is for objects out in space. So let's say we have the Earth here. We have the Earth here, and we're going to look at the very center of the Earth, and let's say we have the moon out here. The moon right there, and of course we are going to be looking at the center of the moon. We usually look at from the center object to the center object. So what is happening is that the Earth is pulling on the moon with a gravitational force, F of capital G. It's just that the moon is actually moving with a tangential velocity, and due to that tangential velocity, even though the Earth is pulling on the moon, it doesn't crash into the Earth. And we feel the effects of the moon on the Earth as well, thanks to the tides, but it's very, very small. But the moon is being pulled towards the Earth. So the idea is there's still gravitational potential energy there, all the way out in space. And so if we start off with this original formula, Ug equals mgh, where the object that will be falling will be m for the moon. Just put a little tiny little m there. Okay, that's like my subscript. We can come up with the new version of the gravitational potential energy starting from here. So the new version, because we're out in space, let's use that capital G. Okay, we have the mass of the moon, and instead of G, we're going to use the gravitational field formula that I showed you before. Okay, times, and we're not going to say h here because we're not looking at a height between those two dots, but rather a radius of r. So times r. And if we do some algebra there, okay, we will get G, m1 or me, m2 or mass of the moon, r in the numerator, r in the denominator. Okay, one of those r's cancels out, so that gives us a r. But there's actually a negative there, okay? And we're going to go over the reason why that negative exists. So right there, for your notes, that is the official formula, of the gravitational potential energy, where your G is not constant. Okay, so let's go over the reason why that negative has to exist. All right, so here we have the Earth, and here we have the moon. So we just discussed that the further away that the moon gets, okay, so like all the way out here, the G is very weak. Now, if your G is very weak, and we are looking at this formula here, mgh, if your G is very weak, that's essentially a value of 0. And so if your G is 0, your gravitational potential energy out there is also essentially 0. So we say that UG is equal to 0 joules when we are super far, or when your R is approaching infinity, basically when there's nothing else around you. Okay, so the idea is, in order for the moon to go all the way out there, okay, what do we have to do to the moon? So we have to do work to the moon. So we have to push the moon. We have to give it some kinetic energy. We have to say, moon, get out of here, right? And so we would push the moon, and so we would speed up the moon until it gets super, super, super far away, almost like a blasting off of a rocket, okay? So when we make the moon go super far away, we are giving the moon kinetic energy. So we give the moon kinetic energy. And we also discussed that kinetic energy can only be positive because 1/2 mv squared, that velocity squared, will always give us a positive value. So now let's think about it. All the way out here, we have 0 joules, okay? But we're giving this moon positive kinetic energy. So the only way that we can reach 0 by adding something positive is if we start off with negative potential energy. And that, my friend, is where the negative comes from. Okay? So the negative comes from the fact that mathematically, and also in terms of calculus, okay, in order to reach a potential energy of 0 joules, you have to go from a negative number and you have to add positive kinetic energy. And if you do that and you shoot the object off into the far recesses of the universe, it'll have 0 joules. And so graphically, what that looks like will be something like this. U and R. So all the way out here, we have 0 potential energy, and we start off with some negative potential energy, and it kind of curves upwards like so. Okay? And this is what we call a potential energy curve. So we can see here, the closer the object gets to the planet, it's going to kind of be like sucked in towards the planet. It kind of falls and rolls towards the planet there, okay? Because the gravitational potential energy just get that. It gets so much bigger. It gets so much stronger. All right. I'll see you next time. Bye-bye.